At the exact center of our galaxy, 26,000 light years from where you're sitting right now, there is an object that physics says should be among the most predictable things in the universe. A supermassive black hole, 4 million times the mass of our sun, sitting quietly at the heart of the Milky Way, mostly dormant, occasionally flickering, as small amounts of gas fall into it. We've had a direct image of its shadow since 2022, when the Event Horizon Telescope captured it for the first time. We understand its mass, its spin, its basic behavior. It has been, for the most part, the well-behaved centerpiece of a galaxy that has learned to live around it. For the past several months, it has stopped behaving. Multiple observatories, working independently and using different instruments and different wavelengths, have detected something emanating from the galactic center that does not fit the established pattern of behavior for Sagittarius A star, the name astronomers gave to our galaxy's central black hole decades ago. Not a single flare, not a one-time anomaly that can be written off as an unusual but explicable event, a sustained, evolving signal that has researchers checking their instruments, rechecking their data, and increasingly talking to each other in tones that suggest genuine uncertainty about what they're looking at. I want to walk through what's actually been detected, why it's different from anything we've recorded before from this region, and what the leading explanations are, including the ones that most scientists are still hesitant to say out loud in public. To understand why this is significant, you need to understand what normal behavior from Sagittarius A star actually looks like. Our galaxy's central black hole is, by the standards of supermassive black holes, remarkably quiet. Many supermassive black holes at the centers of other galaxies are what astronomers call active galactic nuclei. They're constantly devouring large amounts of surrounding gas and dust, producing enormous amounts of radiation, sometimes outshining their entire host galaxy. Sagittarius A star is nothing like that. It's been described by researchers as a remarkably underfed black hole, consuming only a tiny fraction of the material available to it. Its activity is mostly characterized by occasional flares, brief flashes of X-ray, and infrared radiation that occur when small clumps of gas or dust fall into the black hole's immediate vicinity. These flares typically last minutes to hours, occur somewhat unpredictably, and have been studied extensively by telescopes, including Chandra, NuSTAR, and the Event Horizon Telescope. They're interesting, scientifically useful for understanding the immediate environment around the black hole, but they're not mysterious. We understand the basic physics behind them reasonably well. What's been detected recently is categorically different. Beginning in data collected over several months, multiple research teams identified a signal that doesn't match the flare profile. Instead of a brief spike followed by a return to baseline, the emission has been gradually increasing in intensity over an extended period, with a spectral signature, meaning the distribution of energy across different wavelengths, that doesn't match any previously catalogued type of activity from this region. The Chandra X-ray Observatory recorded an unusual sustained increase in X-ray emission from the immediate vicinity of the black hole. Independently, radio observations using the Atacama Large Millimeter Array detected changes in the polarization and structure of emission from the same region. Polarization being a property of light that can reveal information about the magnetic field structure and the physical processes generating the radiation, and infrared observations, conducted using ground-based telescopes equipped with adaptive optics to compensate for atmospheric distortion, have recorded changes in the brightness and structure of the immediate environment around the black hole that don't match any previously documented pattern. 3 different observational techniques, 3 different wavelength ranges, 3 independent research teams, all detecting something unusual happening at the same location around the same time period. The first and most cautious explanation researchers considered is also the most mundane. This could simply be an unusually large and sustained accretion event. Black holes do occasionally consume larger than typical clumps of material, and the resulting emission can, in principle, last longer and behave differently than the brief flares typically observed. There's a famous precedent for this. In 2014, astronomers tracked a gas cloud called G2 as it approached Sagittarius A star, anticipating that its close encounter with the black hole would produce a dramatic increase in activity as material was stripped away and consumed. The anticipated fireworks didn't really materialize. G2 turned out to be more compact and resistant to disruption than expected, and the encounter produced less dramatic effects than predicted. But the event demonstrated that material falling toward the black hole can produce sustained, evolving signals over periods of months, rather than the brief flares typically observed. If what's being detected now is a similar but larger accretion event, perhaps an unusually massive gas cloud, or even a smaller object, like a low-mass star or substellar object, being gradually disrupted and consumed by the black hole's tidal forces that would explain a sustained, evolving signal without requiring any new physics. The problem with this explanation is the spectral signature. The energy distribution of the detected emission doesn't closely match models of typical accretion processes, even unusually large ones. Researchers have run the data through standard accretion models, calculations that predict what kind of radiation should be produced when matter falls into a black hole at various rates, and the fit isn't good. The signal carries an energy signature that suggests a different underlying process, or at minimum, accretion physics, operating under conditions that our standard models don't fully capture. The second explanation under serious consideration involves something that sounds more exotic, but is grounded in well-established physics: a tidal disruption event involving an object more substantial than typical accreted gas clouds. A tidal disruption event occurs when a star passes close enough to a black hole that the black hole's gravity overwhelms the star's own gravitational cohesion, tearing it apart. The disrupted stellar material doesn't fall into the black hole all at once. Instead, it forms a stream that gradually spirals inward, producing electromagnetic radiation that can be observed for months as the material is slowly consumed. These events have been observed and studied extensively around supermassive black holes in other galaxies, and they produce signatures that evolve over exactly the kind of timescale being observed at the galactic center right now. If a star, even a relatively small one, like a low-mass red dwarf, has been tidally disrupted by Sagittarius A star, the resulting signal could plausibly match much of what's being observed. A sustained, gradually evolving emission across multiple wavelengths, inconsistent with simple gas accretion, but consistent with the slow, ongoing consumption of disrupted stellar material. This explanation has gained significant traction among researchers because it doesn't require new physics. It requires an event we've observed elsewhere in the universe, just happening. For the first time in recorded astronomical history, at the center of our own galaxy. If confirmed, it would be an extraordinary scientific opportunity. A tidal disruption event close enough to study in unprecedented detail, providing data quality that observations of similar events in distant galaxies simply cannot match. But there are complications. The orbital dynamics around Sagittarius A star are reasonably well mapped for known stars in the immediate vicinity, and no known star appears to be on a trajectory consistent with the kind of close approach required to trigger a tidal disruption. This doesn't rule out the explanation. There could be an undetected object, perhaps a faint star or a compact remnant that wasn't previously catalogued, but it means the tidal disruption explanation requires either an unidentified object or an unusual orbital configuration that researchers are still working to characterize. The third explanation is the one that has generated the most discussion in specialist circles, precisely because it touches on one of the most actively debated questions in galactic astrophysics: the population of compact objects, black holes, neutron stars, and other dense remnants that are believed to cluster densely around the galactic center, but that we have almost no direct way of detecting. Theoretical models of galactic dynamics predict that the region around a supermassive black hole should accumulate an unusually dense population of stellar mass black holes and neutron stars over cosmic time through a process called mass segregation, where heavier objects gradually sink toward the gravitational center of a star cluster through repeated gravitational interactions. Some models predict that the central parsec of our galaxy, an extremely small region by galactic standards, but enormous compared to the black hole itself, could contain anywhere from several hundred to over 10,000 stellar mass black holes. These objects are, by their nature, almost invisible. A stellar mass black hole, with nothing actively falling into it, emits essentially no radiation. We can really only detect them when they interact with something else, when they merge with another compact object, producing gravitational waves, or when they capture and disrupt a passing star or gas cloud. If what's being observed at the galactic center is the result of an interaction between Sagittarius A star and one of these smaller compact objects, perhaps a smaller black hole spiraling into the supermassive one, or being disrupted in close proximity to it, this could produce exactly the kind of complex, evolving, hard-to-model signal currently being observed. Gravitational wave detectors, including the ground-based LIGO and Virgo observatories and the developing space-based LISA mission, are specifically designed to detect signals from merging compact objects And researchers are actively cross-referencing the electromagnetic observations from the galactic center against any unusual gravitational wave signals from the same time period and general direction. This explanation is exciting precisely because it would provide observational access to a population of objects, the hidden black hole population around galactic centers, that has been almost entirely theoretical until now. Confirming this scenario wouldn't just explain the current signal. It would open an entirely new observational window into one of the most poorly understood populations of objects in the galaxy. There is a fourth possibility that almost nobody in the mainstream astronomical community is willing to advocate for publicly, but which has come up in informal discussions and which deserves to be mentioned with appropriate caveats, because intellectual honesty requires acknowledging the full range of hypotheses being considered, even speculative ones. Some researchers working on the more theoretical end of black hole physics have raised the possibility that the signal could be related to quantum effects near the event horizon, potentially connected to the same kind of anomalous emission that other research teams have separately reported observing around other black holes, including, notably, recent controversial findings involving structured emission patterns near event horizons elsewhere in the universe. This is, to be clear, the most speculative explanation under discussion, and the researchers raising it are careful to frame it as one possibility among several, not as a leading hypothesis. The mathematics, connecting quantum gravitational effects to observable, structured electromagnetic signals from black hole event horizons is, at best, an active and unsettled area of theoretical physics. But the fact that this explanation is being discussed at all, that serious researchers are willing to consider it as part of the range of possibilities, rather than dismissing it outright, tells you something about how unusual the current observations actually are. So what happens next? This is where the story, for now, remains genuinely open. Observatories around the world have increased their monitoring frequency of the galactic center, attempting to track how the signal evolves over the coming weeks and months. If it's a tidal disruption event, the signal should follow a predictable decay pattern, as the disrupted material is gradually consumed, a pattern that's been characterized in detail from observations of similar events in other galaxies. If it's an interaction with a compact object, gravitational wave observatories may eventually detect a corresponding signal, providing independent confirmation. If it's an unusually large but otherwise ordinary accretion event, the spectral signature should eventually settle into a pattern that matches established accretion physics, even if it took an unusual path to get there. Right now, the honest scientific position is that we don't know. The data is real. The anomaly is confirmed across multiple independent observational methods. And the leading hypotheses range from an extraordinary but explicable astrophysical event happening for the first time, close enough for us to study in detail, to something that may require us to revise our understanding of the physics operating in the most extreme environment in our galaxy. There is something genuinely remarkable about the position we're in right now, and I think it's worth sitting with for a moment. The center of our galaxy is 26,000 light-years away. The light and radiation we're detecting left that region millennia before human civilization existed in any recognizable form. Whatever is happening there, whether it's a star being torn apart, a smaller black hole spiraling into our galaxy's central monster, or something we don't yet have a framework to properly describe it, has already happened. We are watching, in real time, the arrival of information about an event that occurred in the deep past, at the literal heart of the galaxy we call home. And for the first time in the history of astronomy, we have the instruments across X-ray, infrared, radio, and potentially gravitational wave observations to actually characterize this kind of event in detail, rather than simply noting that something unusual happened and moving on. Whatever the explanation turns out to be, this moment is a reminder of something that's easy to forget in ordinary life. The universe is not a static backdrop. It is active, dynamic, and capable of surprising even the people who have spent their careers studying its most extreme objects. The center of our own galaxy, the gravitational anchor of everything we call home, from the sun to the earth, to every star you've ever looked up and seen, is doing something right now that nobody fully understands. We are watching, the data is coming in, and somewhere in the coming months, an answer will emerge that will tell us something new about the most powerful object in our galactic neighborhood. The center of the Milky Way still has secrets. We are about to learn one of them,